Okay, so now we're going to look to see how we can analyze. Hold on one second. How we can analyze some of the iterative schemes we've looked at so far, given the framework from the last video. So, to remind you, we have the system that we care about. AX is equal to B, and then we can precondition it. So in the case of Jacobi method, we precondition it to get to D inverse AX is equal to D inverse B. We sort of think about this as being in the form LX is equal to Y. The Richardson iteration is XK plus 1 is equal to XK plus Y minus LXK. And then this converges if the spectral radius of T, which is I minus L, is less than 1. Okay, and the whole idea with this preconditioning, the whole idea with this preconditioning is that we end up with a thing here where the spectral radius is better than the unpreconditioned system. Okay, so if we just try to apply Richardson iteration directly to this, oftentimes I minus A, L would just be equal to A, I minus A would have a spectral radius bigger than 1. And so we apply the Richardson iteration to a preconditioned system where the matrices have better spectral properties. Now, this is not necessarily how the Jacobi method was first conceptualized, but now we can conceptualize the Jacobi method as that, and I think that conceptualizing that way helps us analyze why Jacobi is better than just the iterative method applied to this, why Gauss-Seidel is better than Jacobi, why SOR is better than Gauss-Seidel, because each time when we precondition, the corresponding matrix has a better spectral property. So as I said in the previous video, and as you'll do on the homework, you're going to show that if L is equal to A and A is a Poisson matrix, the spectral radius of I minus A is going to be bigger than 1. What I want to show in this video is how we can guarantee that if in the Jacobi iteration, how we can guarantee that's going to converge. Okay, I've got good news and I've got bad news, and we're going to see about what that is as we go on. Okay, so let me just remind you of a couple of things. If we have a matrix norm, so look in the book to remind yourself of what this definition is. Then rho, the spectral radius of the matrix A, let me use M just as a different symbol, is going to be less than or equal to M in that matrix norm. So what this means is that if I can find any matrix norm where the matrix norm of I minus L is less than 1, then I know I'm going to have the spectral radius is less than 1, in which case it tells me that the method is guaranteed to converge on any beginning input. Okay, so this is a very good thing to know. So what are some necessary conditions? So we're going to look at a particular matrix norm, the infinity norm. Now, the infinity matrix norm, okay, when we talk about vectors and we say like the 2 norm, this means we take all of the entries, add up the square of their moduli, and take the square root. That's the 2 matrix. That's the 2 vector norm. The infinity vector norm is we look at the absolute values of each entry in the vector, and the biggest one of those is going to be the infinity vector norm. Now, the infinity matrix norm is the norm induced by those vector norms. Okay, so what that means in the case of a matrix, the infinity matrix norm is going to be equal to the maximum. So what we're going to do is we want to look at all of the row sums. So the maximum I in the set 1 to n, and we're going to look at the row sum, which is going to be the sum j equals 1 to n of the absolute value of m ij. Okay, so I tells us the row, so we're fixing the row and taking absolute values and summing across. We're doing that for each row. The biggest of those is going to be the infinity matrix norm. Okay. So here's my claim. So if we can prove that the infinity matrix norm of I minus L is less than 1, then what we've done is we have proven that the spectral radius of that matrix is less than 1, and therefore the method converges. Okay. Sorry, I just lost my place in my notes here. Okay. All right, okay, so recall a matrix is diagonally dominant if, okay, so what this means, I'm just going to say what it is and then write it out. It means if you look at every single row and you sum up the absolute values of the off-diagonal entries, it's going to be strictly less than the on-diagonal entries. So, recall a matrix is diagonally dominant if the sum j equals 1 to n, j not equal to I, of the absolute value of m ij is strictly less than the absolute value of mii. Okay, that's what it means for a matrix to be diagonally dominant. It means that the off-diagonal entries contribute a much smaller amount, in this sense, to the matrix than the diagonal entries. Okay, so, and the strict inequality there, as we will see, is going to be very important. So it's not less than or equal to, it's less than. The strict inequality is important. Okay, so write down this definition because I'm about to erase it and we're going to come back to it. Okay. Okay, so here's my claim. If A is diagonally dominant, then the infinity norm of I minus d inverse A infinity is less than 1, and that's the main thing that I'm going to prove, and this implies that the spectral radius of I minus d inverse A is less than 1, and I'm not going to write it, but that would imply that for this matrix, the Jacobi iteration method is going to converge. Okay, so what is the proof of this? Well, let's think about this product of D inverse A. So we're going to think about the product of D inverse A. Now, something that is very helpful is that D is a diagonal matrix, and so its inverse is just going to be dividing by, it's going to be the diagonal matrix where the entries are going to be 1 over the diagonal. Another thing that we need to assume here, which is implied by diagonal dominance, is that none of the diagonal entries are going to be equal to 0. The only way, so the diagonal dominance inequality could not hold in the strict sense if the diagonal is equal to 0. So none of the diagonal elements are equal to 0, which means we can always divide by them. Okay, so what this tells us is that the entry in the ith row and jth column of D inverse A is, okay, so we want the ith row and the jth column. So we want the ith row and the jth column of D inverse times A. Okay, so if we are looking in the jth column, it means we're going to be thinking about the jth column of A. Because remember, the way we define the matrix product the jth column of the product is going to be the left matrix times the jth column of the right matrix. Okay, so if I'm looking in the jth column of D inverse A, I'm going to be thinking about the D inverse times the jth row of A. Okay, so D inverse times the jth row of A. Okay, so what is D inverse times the jth row of A? Well, sorry, the jth column of A. D inverse times the jth column of A. Well, this matrix is almost all zeros. So the only time when I do D inverse times the jth entry of A, sorry, the jth column of A, that I'm going to get a non-zero is going to be in the jth column of D. So I'm going to get Aij, in the ith column, if I'm looking in the ith row in the jth column, it's going to be Aij over Aii. Okay, because Aii is a corresponding entry in D inverse. Okay, so this is what the entry in the ith row in the jth column of A is going to be. Okay, so again, if I'm looking in the jth column, it means I'm doing the D inverse times the jth column of A. And if I'm looking at the ith row, it's just going to be whatever you get basically when you do the ith row of D inverse times doing the dot product of the ith row of D inverse and the jth row of A. Okay, so maybe let me even write this out a little bit more explicitly. So ith row of D inverse and then do the dot product with jth column of A. Okay, now the ith row of D inverse is just going to be the almost entire zero vector except for in the ith column, and it's going to be, what is the, again, D inverse is a diagonal matrix where the entries are 1 over the diagonal of A. Okay, so we're going to have from this 1 over Aii, and then we're going to we're doing the dot product with the jth column of A. So it's going to be, there again, there's only one non-zero entry in this row right here, and it's going to correspond to the ith column. So when we dot it with the jth column of A, it's only going to be the jth row of A. So we're going to have, or the ith row of A. Hold on, let me just write this. Aij. Okay, so again, one more time. Maybe I'm over-explaining this. The ith row of D inverse, okay? If I think about what the ith row of D inverse is, it's going to be almost all zeros because the diagonal matrix is almost all zeros. This row is going to be almost all zeros except for the ith entry. And in the ith entry, there's going to be 1 over Aii because D inverse is just 1 over the entries of D. Okay. Now, when I do the dot product here, if the only non-zero entry is in the ith entry of this row, when I multiply it by the jth column of A, the only entry of this vector that gets seen in the dot product is going to correspond to the ith row. So Aij divided by Aii. Okay, so the entry in the ith row and the jth column of D inverse A is going to be 1 over Aii times Aij. Okay, so now let's think about how I can fix this, because I don't care about the rows or the entries of D inverse A. I care about the entries of I minus D inverse A. So let's say I do I minus D inverse A. And I want to know what the jth entry of that vector, I want to know what the jth entry of that matrix is. Okay, so I is going to be, it's ones on the diagonal and zeros everywhere else. Okay, so what this means, when I do I minus D inverse A, what am I going to get? Well, if I'm off of the diagonal, D inverse A is not going to be affected by that. Right? I'm just going to have minus that. If I'm on the diagonal, it's going to be 1 minus whatever I have here. But if I'm on the diagonal, that is, if I is equal to j, I just get 1. Okay, so what this tells me is that when I do I minus D inverse A, if I do I minus D inverse A, I'm going to get minus Aij divided by Aii if I is not equal to j. And I'm going to get 0 if I is equal to j. Okay, so I'm going to get minus Aij over Aii if I is not equal to j. Otherwise, I'm going to get 0 because it's going to be 1 minus Aii over Aii. Okay, so let me write that up here. Okay, so the ij entry of this matrix, I minus D inverse A, is going to be equal to minus Aij over Aii if I is not equal to j, and it's going to be 0 if I is equal to j. Okay. So in other words, in this matrix right here, the difference of these two matrices, the diagonal is going to be 0, and the off diagonal is given by this formula here. Okay, so now for any row, for any 1 less than or equal to I less than or equal to n, okay, let's see what's going to happen. So I want to show that in the infinity norm, this matrix, the infinity norm of this matrix is less than 1, which means what I need to do, one of the ways that I can prove this, is show that the row sum of, if I look at the row sum of any row, it's always going to be less than 1. Okay, because remember, the infinity norm is you look at all of the row sums and take the absolute value, look at all of the row sums and take the maximum of that. That's the infinity norm. And remember, when I say row sum, I mean we sum up all of the entries, we sum up the absolute values of all of the entries in the row, or sum up the moduli of all of the entries in the row. But all of our matrices are going to be real, so the row sums, we're just summing up the absolute values of each entry in the row. Okay. So if I look at any I, this tells me what the formula for the ij entry is. So I'm going to look at the sum j equals 1 to n of I minus D inverse A ij. Okay, this is my formula right here. And I actually want the absolute value of this. So this is going to be the sum j equals 1 to n. I'm summing up over all of these things, the sum j equals 1 to n. I'm summing up over all of these things, but notice when I is equal to j, I don't have a sum. So I'm just going to write this j does not equal to I, and we're going to have the absolute value of Aij divided by Aii. Okay, now Aii, that doesn't depend on j, so I can move this out of the sum. And so this is equal to 1 over the absolute value of Aii times the sum j equals 1 to n times the absolute value of Aij. Okay, now by diagonal dominance, I know this here in that circle is strictly less than 1. So this is going to be less than 1. Sorry, no, this is not strictly less than 1. And the circle is strictly less than the absolute value of Aii. So then this right here is going to be strictly less than 1 over Aii times the absolute value of Aii, which is equal to 1. So in other words, this quantity right here is strictly less than 1. Okay, so now what that tells me is that the infinity norm of the T matrix, that is I minus D inverse A, the spectral norm of the iteration matrix is less than 1 because the infinity norm of the spectral infinity norm of the iteration matrix is less than 1. Okay, that's if A is diagonally dominant. Okay, so that's the good news. If you have a matrix, you don't have to do much to show whether or not it's diagonally dominant. So it's very, in some sense, it's easy maybe to see if a matrix is diagonally dominant. Maybe not necessarily from a computational point of view, though also that's easy, but from a construction point of view, if you have a matrix that you're constructing, it can be easy to tell whether or not it's diagonally dominant. Here's a bad thing. What is a Poisson matrix? What are the rows of the Poisson matrix? It's -1, 2, -1. Is that diagonally dominant? No. If you add up the off-diagonal entries, you get, if you add up the absolute values of the off-diagonal entries, you get 2. The diagonal is equal to 2. So the Poisson matrix is not strictly diagonal dominant. We say it is weakly diagonally dominant. But notice, if it was only weakly diagonal dominant, then what would change over here? This would no longer be strictly less than. It would be less than or equal to. We would have less than or equal to here, and in fact, we would now say that the infinity norm is less than or equal to 1. And in fact, it would be equal to 1 in the case of the Poisson matrix. Okay, so the infinity norm of, if I look at the Poisson matrix, if A here is a Poisson matrix, the infinity norm of this matrix is equal to 1. Now it turns out, as we will see, the spectral radius of the Poisson matrix, or the spectral radius of the iteration matrix for this Poisson matrix is less than 1. Okay, but we can't prove that by comparing it with the infinity norm. So that's the bad news. On the other hand, we really want to know what the exact value or a better estimate for the spectral radius of a matrix is, because that's going to tell us how fast the matrix, or how fast the iterative method converges, and we are going to look at that in upcoming videos. In the next video, we're going to apply a similar analysis to the Gauss-Seidel matrix.